Okay, so we have our Mr. G 10.1 worksheet, so let's take a look at this. And so it says the first question is about conservative forces. So what does that even mean? So conservative forces do not depend upon the path they take. An example of that is force is any force of gravity, so work done against gravity. So let's just say that I had a mountain that I needed to get to the top of. And so I know that I want to lift a weight. I want to, take a weight from the bottom of the mountain and get it to the top of the mountain. And I know that gravitational potential energy is the force due to gravity times the change in the height. So I can literally go straight from the bottom all the way up, straight line, straight to the top in the shortest path, or I could go kind of switchbacks up the mountain like that. But the path that I take does not matter. The change in gravitational potential energy only depends on the change in height. So we say that's path independent, that it does not matter the path that we take. Friction is what's called a non-conservative force. When we're dragging or sliding against friction, then the path that we take totally does matter. And so if we consider, for instance, our hill, if we're doing work versus gravity, it's just a question of the change in height. It doesn't matter what path we take. But if we do work against friction, then it does matter the path we take. So those two paths, like the straight up path and the curvy path, if I was just doing work against gravity, it wouldn't matter which one I took, but if I was doing work against friction, then the shorter path would be better. And so we know that work is force times displacement times the cosine of the angle between them. And so we can just take these, we can take these paths just as direct legs where the force and the displacement is in the same direction, so we don't have to worry about cosine theta. And so we know that the force of friction is the coefficient times the normal force. Normal force on a flat surface is equal to the weight of the object. Weight is mg. And so we wind up with friction force for any of the paths chosen. Use G is 9.78. I just noticed that. Why? Really? Okay, glad I read the problem. Here, let me fix my numbers. All right, there we go. So the friction force along those paths is going to be 55.0125 newtons. And so we just use the distances that are given because we know that friction is path dependent. And so for the legs, we know one leg is 6.75 meters and then the angle is 25 degrees. So we get to do some fun right triangle trigonometry because why not? Of course, I don't know why the numbers are so strange, but whatever, we now have the dimensions of our triangle. And so if we run W equals FD for friction, so when we run just the hypotenuse, we get 410 joules against friction, but of course with the longer path of the two legs, we have two legs, so we're going to do FD twice. And so when we do the legs, we wind up with 544 joules. It says state whether friction is a conservative force and justify your statement. The answer is no, it is not, because it does depend on the path. The longer the path, the more work is done against friction. I just realized I've been writing these solutions without actually saying anything. So, number 2, why is the field view preferable to the action at a distance view of forces? It's a weird question, and I was looking into it, and I don't know what Gysbers is really getting at by saying that it's preferable. I do know that the field view is now the accepted view when talking about gravitational and electromagnetic forces. Electromagnetic forces are still mediated by a force carrier being the photon, and the photon still travels at the speed of light. So what I've read is that the action at a distance view, the force was also propagated at the speed of light. So I don't really see what the difference is there. But I do know that in terms of gravity, now astrophysicists really are starting to think that gravity may not even be a force at all, and that objects may simply warp the space-time that they're in. and that the response of other masses is as if there were a force. But it would also explain why gravity only attracts and does not repel, because it's a question of a space-time warping. For another thing, I had heard that when they talk about quantum entanglement and how if you tweak one particle, a particle that is entangled with that one particle reacts instantaneously faster than the speed of light, that kind of violates laws of physics. Except now physicists are starting to think that it's possible that that quantum entanglement is actually happening through a space-time connection. That there's maybe even kind of like a wormhole, yeah, you heard me right, a little tiny wormhole between those two little particles, allowing for like a space-time tunneling between the two particles, which is bizarro, but it would also allow for that there's no violation of the speed of light. The fact that space-time itself is being warped between the 2 points means that the information doesn't have to travel faster than light. Maybe that's a little bit convenient, but it is a cool theory. But yeah, so physicists are using field view more now than action at a distance of view. Number 3, so we have a field as drawn there. And it says, what physical quantity is the cause of this surface? And so that it's not shown as a well, but as a peak. And so we consider wells to be either negative charges or masses in a field. A peak, an inverse well, if you will, is a positive charge. And then for number 4, if I popped a negative charge there, it would be attracted to the positive charge, so it would move towards that hill. Number 5, electric field lines between oppositely charged parallel plates. Oppositely charged parallel plates have an evenly spaced field between them, meaning that at any point between those two parallel plates, the field is the same field strength at all points. That's worth noting. So yeah, the electric field between oppositely charged parallel plates is constant. And so it says justify the electric field strength is constant between the plates by referring to the sketch. And so the sketch shows evenly spaced field lines. The way electric field lines are drawn is that the closer the lines are together, the stronger the field is there. And so if I draw evenly spaced lines, then there is no difference across the field in strength. It's the same strength at all points. And then finally, number 7, it says sketch 3 equipotential surfaces. Equipotential surfaces are surfaces or lines that are all joined points of the same voltage, the same electric field strength, and they are perpendicular to field lines. So just to distinguish between the field lines and the equipotential lines, I made those in blue. It said I wanted 3 of them, so I drew 3 of them. So for number 8, it says potential difference between 2 plates is 25 volts, which is the potential difference between each adjacent pair of surfaces that you sketched in terms of the equipotential. So assuming there's a potential difference of 25 volts, maybe one plate's at 25, positive 25, and then the other plate is at 0, or maybe it's grounded, and so there'd be a potential difference between 2 plates of 25 volts. As you go from the 25 volt plate to the 0 volt, you have a steadily changing gradient of voltage going from 25 to 0. So maybe that center line would be like 12.5, and then the in-betweens would be like maybe this guy over here would be half of that, so maybe like 6.25 volts, and then this guy over here would be maybe like 19 volts. Sorry, make that 18.75 volts. So yeah, the voltage, the potential difference, since it's a evenly spaced field, the potential difference is going to drop gradually, change gradually from one plate to the other. Of course, the lines that I drew, maybe the lines, the center line is fine, but maybe the other 2 lines might be a little bit closer to the plates. But I think you get the idea. And so between each adjacent pair of lines, I was using 6.25 volts there. which would actually match up with like an answer key because they did ask for 3 lines. I'm thinking of redrawing the lines, I just don't have it in me. So, last question on this page, number 9, gravitational potential difference. Well, we know that electric potential difference is in an electric field. Let's say V electrical is the work done against an electrical field, I guess you would say WE, per unit charge trying to move. So gravitational potential difference, V sub G, is the work done against gravity moving a test mass in an electric field. I guess if they're saying define, it's not good enough to write the equation. You should actually describe what the heck you're talking about. So let's do that. The gravitational potential difference is the energy difference between 2 points in a gravitational field per unit mass. That's different than gravitational potential. Gravitational potential, this is a firm definition here, is the work done per unit mass and moving that mass from infinitely far away to point P, which sounds kind of goofy, like infinitely far away. And yeah, that's true. It's really kind of like if you do like the force times the displacement, it's kind of like if you're infinitely far away, it's kind of like the gravitational field strength there is 0. So, like, you're taking, like, the integral, the sum of all of that work that was done from infinitely far away to that point. That's kind of like where the infinity comes in, because it's actually, like, an integral. But anyway, so there's number 9. Let's continue on with number 10. Okay, number 10. So we are drawing the gravitational field for a point mass. Those would be arrows pointing inwards, evenly spaced. And then it says equipotential surfaces around that point mass. And I've been thinking about equipotentials and how it's important how they're drawn. So I want to give this parallel plate diagram another go. I was satisfied with my previous version of the field lines where they were evenly spaced. I was not totally satisfied with the equipotential lines, and it does actually matter. And so the equipotential lines follow the same principle as the electric field lines. The stronger the electric field is, the greater the line density, so the closer together the field lines are. Same is true of the equipotential lines. The stronger the field, the closer the lines are together. So if the field is uniform, if it's pretty much constant, then the spacing of the equipotential lines should also be pretty much constant. So it did ask for 3 lines, so I'm going to draw a center line. There we go. And then the 2 other lines, I drew earlier I drew them a little close to the center line. I want to pretty much draw them in between that center line and the surface of the plates. Remembering that for the edge effect lines, I'm still going to be perpendicular to the edge effect lines, and so it's going to be like perpendicular to the edge effect lines, kind of there and there, but then that guy, oops, where's my eraser? Eraser, there we go. That's pretty good. There we go. And then this guy, oops. There, I think that's fair, evenly spaced. And then the values, I also erased the values, so let me fix that, put those values back. I'm not really sure why they didn't use a number that was evenly divisible, but they said 25 volts and a potential difference from plate to plate of 25 volts, meaning that this negative side will be at 0 volts, so that the difference between them is 25 volts. And so as we go across the field, the voltage changes proportionally. So in the middle here, we would have 25 divided by 2, that would be 12.5 volts. And then half of that is 6.25 volts. And then in between 25 and 12.5 would be 18.75 volts. So there we go. And again, I'm getting this, it's like, where are these numbers coming from? Going from 25 to 0 with evenly spaced gradations, meaning that in the middle I would have half of the field, and then at the 3/4 point and at the 1/4 point, it would be 3/4 and 1/4 of the field. So there we have it. Now let's go back to that gravitational field that I was about to draw. So here it wants to sketch the gravitational field lines and the equipotential surfaces that go with those field lines. So the field lines would have evenly spaced arrows pointing inward toward the mass. Inward pointing lines. It kind of looks like a snowflake. So that would be the gravitational field lines for the mass, and then for the equipotentials, basically it's going to be circles, because if I have I have like radial lines from a point, perpendicular to those radial lines is going to be a circle, but we can't draw evenly spaced circles, because as we move away from the mass, the field strength drops off exponentially. So let's see if I could draw a nice set of nested circles. I'm going to use blue again. But again, the circles are not just going to be nested, they're going to be closer together near the mass and further apart farther away. So yeah, those equipotentials are closer together the closer we get to the mass, because the field strength is stronger there. Again, a good analog of this is contour lines on a topographic map. The bigger the gradient in the field, like say like the steeper the mountain, the closer together the field lines are there. So here we have two point masses, and so I drew the inward pointing gravitational field lines, but there's a problem with this. First of all, a comment: the length of the lines does not matter, but how close together the lines are does matter. But we also have a problem, and that problem is there. We cannot have crossing of field lines. That is a no-no. Same thing for here, these kind of like overlapping lines. So we have to fix the field in between the two point masses. Yeah, so instead of the lines crossing, they kind of wind up looking like this. It's almost as if the lines are like avoiding each other. And then again, the equipotential lines are are at right angles to the field lines. And so the equipotential lines would kind of look like that. Kind of looks like a little bit like a peanut. So yeah, one other note that I wanted to point out is that in the center here, the field cancels itself. So it's possible that I could put like a test mass right in between those two masses. And if these were in a three-dimensional sense, if these were both gravitational wells, but wells of the same strength, then in between those wells, you kind of have like a saddle. And so a mass sitting there would not accelerate towards either mass. In other words, it'd be no net force, no net field there. So for what it's worth. Okay, so that's 10 and 11. Then 12, we have W equals FD cosine theta, and definition of gravitational potential difference to show gravitational field strength is G is negative VG over delta H. I feel like they didn't give us a lot of room, so let's zoom in. So here are the arguments. We have W equals FD cosine theta. The potential difference, gravitational potential difference, is work per unit mass, and when I show the gravitational field strength is negative gravitational potential difference over the change in height of an object that has moved in that field. So let's go from there. Okay, so we have our definition of work, FD cosine theta, where theta is the angle between the force and the displacement. We have the gravitational potential difference is the work per unit mass. And then we have that gravitational field strength is negative the gravitational potential difference divided by the change in height. And so we have to be able to show that. And so we know that for FD cosine theta, we know that F, if we're raising an object of mass m against a gravitational field. So that F would be the weight of the object, which is mg, because that's where the mass is coming in. And then theta is actually going to be 180 degrees because the change in height, it's like an upward vertical change away from the Earth, but the force due to gravity attracting that mass is towards the Earth, and so the displacement and the force are in opposite directions. So the angle between them is actually 180 degrees. That's where the negative is coming from, because the cosine of 180 is -1. Yeah, let's maybe note that, right? Cosine of 180 is -1, and so that's why all of a sudden cosine 180 disappears and a negative pops in, right? Because cosine 180 is -1. So we have work is negative mg delta h. And so I take that negative mg delta h and I slip that into delta, the gravitational potential difference is equal to work per unit mass, and so I divide out the mass, and so I get that gravitational potential difference is negative g delta h. If I solve for g, I wind up with negative gravitational potential difference over the change in the height, which is what the problem was trying to show in number 12. So yeah, like I said, they didn't give us a lot of room, so I can zoom to make that happen, right? And here's my little explanation. All right, next question. And so 13, we want the work done by this change in gravitational potential. We know the mass, we know the gravitational potential at A and at B, and so we know that change in gravitational potential is work per unit mass, so we're solving for work. And so we find the difference in gravitational potential, final minus initial, divided by the mass, and we get 0.008 joules. I also just realized something. I'm kind of throwing around this delta VG is work per unit mass. That is in the data booklet under 10.1, written as work is m delta VG. Also, I'm trying to break myself of Regents physics habits. I just realized that in my explanation here, you guys don't use D, you use S. So I keep forgetting that. Let me give that a little fixaroo. Let me change my eraser size here. S. Then I think there's another one over here in my explanation. That's the eraser song. Let's see. Any other D's in here? Nope. So we will replace with S. There. Fixed it. Okay. Alrighty then. Let's get to number 14. Does it matter what path the mass followed in going from A to B? No, because gravity, force due to gravity, is a conservative force. It is path independent. So 15 is pretty straightforward. They give us the charge is negative 15 microcoulombs, and it goes from A, where its potential is 6.75 volts, to point B, with a potential of 8.25 volts, and it wants the potential difference by that move. Well, you just take the difference in the potentials. So 15, the potential difference is 1.5 volts. Then for 16, to get the work done, you just multiply the charge times that potential difference. We wind up with a negative work because the charge is negative. And again, negative work, he said no such thing as negative energy. There's negative energy and negative work based on perspective. You know, if a system does work, that's positive work, it loses energy, so it's negative energy. Or if work is done on a system, it gains energy, but from the perspective of that system that the work was done on, that's negative work. So the work and energy kind of go hand in hand. They trade off, kind of. So did the system gain or lose energy during the movement? Well, the work was negative, so the energy was a gain. It was positive. And so that field, it did positive work on the negative charge, but from the perspective of the charge, work was done on it. So that would be negative work, and so the energy gain is positive. All right, so we have a dipole, positive and negative, and we need the electric field, which I just drew. Closed loops going from positive to negative. Again, I'm not sure I saw anywhere in the notes, but what the field lines actually show is the path a loose positive test charge would follow in the field. And so what the field lines do is, since they're curved, they're not vectors, but what they do is they connect all the vectors in points in the field. So if you had like a vector field, that if you went at any given point in the field and found the vector of that field at that point, that would be a straight line. That would be a vector. But if you then took all of those vectors in the field and kind of connected them up following their trends, you get the field lines. Then, all right, so that's for the dipole. Now it also wants the equipotentials. Man, this is like an art class in here. And then the equipotentials are going to kind of look like that. Their lines are a little closer together in between the two charges in the dipole and a little further apart outside on the other side. Because of the combined effect of the two charges, it's strong in between the fields. We can also see that the electric field lines are closer together in between the two of them. Zooming out, I see the right side extends further than the left side does. Whatever, I don't really care, close enough. And in 19 and 20, it looks kind of goofy. They have some kind of like random shape. I guess they just want you to make sure that you understand the principles. So this is my best crack at what they have going on here. Again, coming out of positive, going into negative, trying to be perpendicular to the surface. Over on the right side, for the negative guy, where the lines would come out of the surface and then cross and then have them diverging away from each other. Now, what is the equipotential going to look like? That's interesting. Maybe something like that. Again, equipotential lines are perpendicular to the field lines. I think Mr. G just kind of made up this shape just to have like a non-standard shape just to see that you understand the principles. It really is kind of funky. All right, well, that's the last question on the Mr. G worksheet for 10.1. Thank you.